we discuss the cylindrical coordinate system. Cylindrical coordinates are a rho, a phi, and a z, where you have rho here, phi is this variable, and z is this variable. Z is the same as the Cartesian z. You have the x, y, z Cartesian coordinates, and rho, phi, and z as the cylindrical coordinates. This coordinate system is used when there is a cylindrical symmetry in the problem. So for systems with cylindrical symmetry, the cylindrical coordinate system yields the governing equations in their simplest form. This is quite important. So the equations arrive in the simplest form if the symmetry elements of the problem are used while modeling them. And this coordinate system is a curvilinear coordinate system. It's not linear like the Cartesian xyz. Cartesian system, the spherical system, and the cylindrical coordinate system are among the most widely used coordinate systems. Other curvilinear coordinate systems do exist. For example, you have the bipolar cylindrical coordinate system and the oblate spheroidal coordinate system, among many others. So let's look at the coordinate surfaces of the cylindrical coordinate system. The coordinate surfaces are rho equal to constant, phi equal to constant, and z equal to constant. So if you look at this diagram, rho equal to constant yields the cylinder, this cylinder. Phi equal to constant yields this plane, and z equal to constant yields the horizontal plane, this one. So those are the coordinate surfaces. So here we show the unit vectors of the cylindrical coordinate systems in this diagram. This diagram also shows the differential curvilinear elements cube formed by differential elements of the rho, phi, and z axis. So if you look at the unit vectors of the cylindrical coordinate system, we mentioned that a rho, a phi, and a z are the unit vectors. So this is the rho direction. A rho is a unit vector along the rho direction. A phi, look at the direction of phi. So a phi is directed that way, and a z is directed along the z axis. Same like the a z of the Cartesian. Let's look at the transformations which connect cylindrical to Cartesian coordinates. So from the geometry of the definition, it is clear that the x, y, and z, the Cartesian coordinates of the point P, may be computed as rho cos phi, rho sin phi, and z. So these are the three equations which describe the transformation from cylindrical to Cartesian. And if the inverse transformations are seen, they are inverse transformations convert cylindrical to Cartesian to cylindrical. So if Cartesian coordinates are given of the point, then its corresponding cylindrical coordinates may be obtained by using these three equations. These are obtainable from the first three equations. That is, cylindrical to Cartesian transformation may be used for computing these three equations, which describe the inverse transformation from Cartesian to cylindrical. Let's look at the surface areas and the volume of the curvilinear differential cube. So using the direction and the unit vectors of the cylindrical coordinate systems, the tiny curvilinear cube may be constructed, the sides of which are shown in this diagram. So d rho is the tiny length along the rho direction, dz is the tiny length, differential length along the z direction, and rho d phi will be the differential length along the phi direction. So we have a curvilinear cube with sides d rho, dz, and rho d phi. So these sides can be used for computing the surface areas. So rho d rho into d phi will be d rho into rho d phi will give us the top surface area. because this side is rho d phi, same as the bottom side, and this side is d rho. The product of d rho and rho d phi will give you the top surface area, which is same as the bottom surface area, not visible in this diagram. Likewise, the volume of the element, curvilinear element, is product of these three sides, which will work out to be rho d phi dz. Now we look at the transformation of vectors between cylindrical and Cartesian coordinates. If A is any vector which is expressed in Cartesian coordinate systems, its representation will be like this. And the same vector A, when expressed in cylindrical coordinates, will have this representation. Here we used, of course, the unit vectors of the cylindrical coordinate system. So in order to get the A rho component, for instance, we need to multiply both sides of this equation with a unit vector A sub rho. Okay, so in the process, A rho will work out to be the A dot A rho as shown here. The A will be the Cartesian A rho. Likewise, A phi term will be obtained by taking the dot product of the Cartesian A with A phi, because the other combinations will be 0. For example, if you look at this, AZ dot A rho and AZ dot A phi will be 0 for getting the A rho calculation. So in the conversions between these two coordinate systems, it is clear that we need the dot product between the unit vectors. So these dot products will allow us to make the transformations between the cylindrical coordinates and Cartesian coordinates. So if you look at the unit vectors of the Cartesian, AX, AY, and AZ, and the unit vectors of the cylindrical, A rho, A phi, and AZ, then the angle between these vectors and the other parameters may be used for expressing the unit vectors of the Cartesian in terms of the A rho, A phi, and AZ. And this matrix here shows exactly these inner products. That is, AZ dot A rho, AZ dot A phi are all contained in this matrix. So this is, for example, AX dot A rho, and so on. So that is, when AX is expressed in the cylindrical coordinate system, then AX will have cos phi A rho minus sin phi A rho and 0 AZ. AY will be sin phi A rho cos phi A phi 0 AZ, and AZ will be 0 0 AZ. So that's the transformation between the unit vectors of the cylindrical and Cartesian coordinates. So this calculation shows how the this table could be used for converting one coordinate system to other coordinate system. The components of any vector can be computed by using this table.